So good afternoon, everyone. Thank you, or actually good evening, good morning, depending on where you're joining us from. So today we have a slightly special occasion because our guest speaker is in China. So this time is actually going to be midnight for him. So he's still very excited to presenting with us, but we will do it slightly differently. We will play a pre-recorded video of our guest speaker presenting his topic. I think Sophia, you're going to introduce us the video as we are getting started. A little bit background about our guest speaker. So he gets his PhD in computer science from University of Pittsburgh and is currently leading a 200 team of software engineers in TAL education group. So that is one of the most prestigious education groups in China. And today he will be presenting us some of the AI related topic that he and his research lab is leading, as well as some of the applications in the products. With all that being said, let's jump right into the video. Thank you.
We built it called the Teacher Question Detections. Tao Liu from Tao Education Group. And my talk today is a practical guide to robust multimodal machine learning and its application in education. I have working in the ed tech field in the past few years, and currently I'm the head of engineering at the Xuesi 111 at Tao. And my research area lies in all aspects of AI in K-12 education. Our experience of the world is multimodal. We see objects, hear sound, and feel textures. Then come up to a decision. Multimodal learning suggests that when a number of our senses are being engaged in the processing of information, we understand and remember more. By combining these modes, learners can combine information from different sources. Especially in this talk, I will focus on discussing learning from multiple modalities, including language, images, and sounds. When it comes to the topic of machine learning or deep learning, a large body of research works are dealing with learning data representations. The effective representation can solve the majority of industrial machine learning problems as well. So in this talk, I would like to share some of our experience about bringing together information from different modalities and achieve better and more effective data representations. Here is the outline of my talk. In the first part, I will talk about our work of multimodal learning for audio and language representations. In the second part, I will share some practical research efforts about robust language learning. Third, I would like to show you some research-driven product we built and then conclude my talk. So this is the first part, multimodal learning for audio and language representations. There are tons of rich information contents in both language and voice. The language focuses on the content, and the voice contains extra emotion and feelings. Information from both modalities are very useful when building practical machine learning applications. Let's take speech emotion recognition as an example. The speech emotion recognition task is given an audio clip of spoken sentence, decide what emotion it is. The traditional approach to handle such multimodal tasks usually fall into the late fusion paradigm. As you can see here, we first get the transcription from the audio signal. Then we extract the sentence level embeddings from both the linguistic and acoustic information respectively. Once we get these embeddings, we directly apply a fusion technique like a concact to get the fused representation and then use it for emotion prediction. So the above approach is simple and effective. However, we would like to make it better. At all, we don't want to unconsciously concat the sentence level embeddings from two modalities. We come up with an idea of conducting fine-grained multimodal learning. Especially, we first conduct the temporal alignment, which, as you can see here, we align the pronunciation of each word in the audio stream. We use existing alignment tools to get the start and the end timestamp of each word in the audio signal, and we apply min and max pooling of min and max pooling operation to extract the word level embeddings from the audio signal. After such temporal alignment min-max pooling operation, we get the same number of word embeddings from both modalities. Once we have the initial embeddings from both audio signal and the transcription, we conduct embedding fusions by cross-modality excitement. Excitement is a trick from computer vision, if I remember correctly. Basically, it works like this: from the view of the language, it finds which part of the voice is important, and also from the view of the speech, it finds which part of the language is important. Specifically, we use a sigmoid function as the excitement function, and we use the embeddings from one modality to compute the excitement weight of the embeddings of the other modality. In such a way, embeddings from one modality are weighted by the importance of the view of the other modality. Here is the overall framework of our approach, which consists of 4 important blocks. So as I colored here, from the bottom, the orange box, it is acoustic and semantic encoders, which encodes the raw data. The second block is the temporal alignment min-max pooling. It aligns frame level acoustic information with token level embeddings. The third block is in green, which is a cross-modality excitement. And the final one is the final prediction part, which is use the fields embeddings to make the final predictions. We validated our approach by 2 commonly used datasets, the AE-mocap and the ReviDAS. These datasets are standard test set for speech emotion recognition. And also we list the experiment settings. So here's the result. The result demonstrates that our approach is superior on the prediction task for multimodal speech sentence, and it outperformed a wide range of baseline in terms of prediction accuracy. So furthermore, we conduct detailed ablation studies to show that our temporal alignment, the min-max pooling mechanism, and the cross-modality excitement significantly contribute to the promising result. As you can see the tables here. Meanwhile, in order to encourage the research reproducibilities, we have open sourced our code at the following addresses. Okay, so in the previous work, I briefly talked about the directed learning embedding fusions from 2 modalities. However, there are lots of work going on beyond that. Nowadays, pre-training becomes a buzzword, and it is prevalent across many research areas. So here I just show you a graph about the standard machine learning workflow with pre-training. Typically, a large-scale model is pre-trained on some unlabeled data such as bird. Then for conducting predictions for specific tasks, we conduct fine-tuning with task-specific dataset, and the objective is optimized with the task-specific loss. BERT is probably the most popular pre-trained language models. Here is a picture I grabbed from the internet, and as you can see here, since BERT was invented in 2018, many improved versions are developed. As you can tell from the model names themselves, lots of existing researchers focus on combining both visual and language informations. Little has been done for utilizing information from audio and the language modality. Here, I would like to introduce a pre-training cross-model transformer we developed at TAO for building practical ML solutions in education scenarios. Here is the overall model architecture of our proposed approach. Our cross-model transformer is built upon the standard encoder-decoder transformer architecture. The left part is standard transformers encoder part, and we don't change it at all. We made several modifications on the decoder part, which is on the right. Okay, so here's the key thing. In our approach, the key component is a thing called multi-head cross-model attention, which builds the intrinsic connections between language embedding and acoustic embeddings. As you can see from the equation here, we use the language embeddings as the key and the values, and then we use the acoustic embeddings as queries in the standard attention formulations. In such a way, we are using the learned language embeddings to represent the acoustic information. In the loss part, we combine the standard mask language modeling loss and the mask cross-model acoustic modeling loss, which is used which uses the weighted language representation to recover the masked acoustic information. With these two loss functions, we do the pre-training for the audio and the language and label data. Once we have the pre-trained models and want to use it for fine-tuning, we apply the standard cross-entropy loss. Meanwhile, in order to capture information from different modalities, meanwhile, in order to capture the information from different modalities, we design an orthogonal regularization. The orthogonal regularization will prefer the representation learned from two modalities dissimilar. Okay, so we conduct the pre-training with two sets of parameters. As you can see here, this will give us two model variants, a base one and a large one. Yeah, our CTL model is evaluated on three well-studied tasks, including the emotion classifications, sentiment analysis, and the speaker verifications. And all the relevant results are listed here, and apparently our model has the best performance. Furthermore, we conduct the detailed component analysis to well understand the proposed model, and due to the time limit, I will check, please, if you want to know the details, please check the details in our AMNLP papers. Okay, in the second part, I will talk about the robust language learning with noises. Yeah, so for the ML practitioners, we all know that building practical ML solution in the noisy environment is very challenging. So here I will show you two video clips about demonstrating very common and typical applications. It's called the auto mental masquerading applications. So as you can see here, we use the phone to take a picture of the student homework, and we can crop the questions, and the OCR will recognize every word here, and it will search the question bank and find the question and show you the answers. So this is called the searching, right? On the left part, which is the images, it will show you if we take a picture of the student homework, it will do the auto grading. And also, lots of companies have already released their math tutor app. As you can see here, I just list the three popular apps made by the big companies. The first one is the PhotoMath, and the second is the Microsoft Math. The third one is Ada, which is made by Pearson. So as you can see here, these three apps are very similar. It kind of take a picture of the student ratings, and it will recognize the ratings. And if it's a question, if it's a problem, it will do the the question will be solved automatically by the programs, and the solution is displayed to the student. Okay, yeah. So this is one AI applications in education scenario there. So here is another one. It's called auto IC gradings. As we all know, the students usually they write a lot of essays when they are in school, right? So the handwriting is very difficult to recognize, and grading this kind of essay is time consuming for teachers. So therefore, there are a bunch of applications driven by the NLP technologies. They will do the auto grading. So here I just took a video from the Grammarly website. So as you can see here, we can upload the essay, and the programs will be the program will grade this essay, right? So it's grade from various dimensions, right? For example, the readability, the correctness, the clarity, the engagement, and so on. Yeah. So this is kind of pretty widely used by a lot of students. Okay. But what is the reality? The reality is very challenging, right? So when the NLP meets the OCR, it's kind of tough. So I also took a picture from the internet. As you can see here on the left part is a kind of a note written by a student. And if we send this picture to the Amazon OCR engines, it will give you the recognized text. But as you can see here, we barely can read this kind of text. It's very horrible, right? So if you want to do some downstream NLP tasks, it's very challenging because the recognized OCR words is terrible. So this brings numerous challenges for the downstream NLP models, right? So existing research work kind of handle this type of errors in two directions. The first direction is do the pre-processing, right? So we design a pre-processing module kind of do the noisy reduction. For example, we can run some Ruby spell checkers, or we can run some machine learning driven or the neural network driven grammar error correction modules, kind of try to correct the errors. And we can even try the kind of the large scale language models, right? The other direction is we can do data augmentation, right? And also we can utilize the power of adversarial trainings. We can use the kind of the white box attack and the black box attack to kind of augment our training data, right? So we can use this way to let the model see a lot of errors and trying to let the model be robust. However, so when we apply those kind of approach in the educational scenarios, they usually don't perform very well. If we look at the problem, one of the biggest problem is all these existing approaches, they don't consider the OCR error distributions. All the errors here from the OCR engine, they follow some distribution. They are not random, right? So that's kind of motivate us to do a little bit better. So I will show you classic examples here about the OCR errors. So here if we look at the top part, the sentence contains the token or character level errors. For example, the I should be a little I, but the OCR show you a capital I, right? And the word an become a, so the letter n is missing, right? So this kind of all this kind of errors happen quite often in the OCR engines. The second type of errors is the kind of the phrase level errors, or we call the span level errors. So I will show you an interesting example, originally in Chinese. Here translation here. So in Chinese, the kind of the phrase means the tortoise meditate. However, in because this kind of word is a little bit similar from their appearance, so the OCR engine fails and it tell you, oh no, this is a jet black box. So as you can see here, the meaning are totally different, right? So the key thing is when you run the OCR engine, the recognition of the current word will affect the subsequent letters, right? So this is a key problem. So therefore, in our work, so we want to do a little bit better, and we design a multi-source OCR noisy simulations. So what we did is we have 3 different ways to simulate the OCR errors, right? So our simulation, our generated example specifically focused on the OCR errors. So the first type of simulation is we call rule-based simulation. So basically, it focuses on the token level errors, and it makes insertion, deletion, and substitution edits to simulate the OCR errors. The second type of simulation is attack-based. So what attack-based does is it will replace some tokens with its synonyms at the weak spot. How do we find the weak spot? We use adversarial training techniques, right? So we're trying to kind of attack the sentence, and we find the weakest spots, right? The third type of simulation is model-based. For the model-based simulations, we train a model to generate the kind of the OCR recognitions, right? So basically, what we do is we use the standard transformer model, which is a sequence-to-sequence neural network models, and we trained the transformer on the parallel data of the human transcription and the OCR transcriptions. So the models will be focused on how to simulate the span level error, which is kind of difficult to simulate from the previous 2 simulation module. Okay, so yeah, we combine all these 3 modules and generate a lot of good training examples. And during the training part, and we have kind of 2 heuristics, which shows us kind of a significant performance gains. So the first heuristic is hard example mining. So what it does is at each iterations, it uses a current model to compute the representation of the noisy-free samples, and also we compute the representation of the simulated version. And then how do they define and select the hard examples? It selects the sample pairs with the largest cosine distance between these 2 representations. One is clean noise, which is noise-free, and another is simulate the noisy one. And we compute the distance between these 2, and we select the largest one, right? The largest one, which means they are kind of dissimilar in the existing iterations, and we're trying to minimize it, right? And the third trick, the second trick is called stability loss, right? So in our work, in addition to the standard cross entropy loss, we kind of add a stability part. The stability part is also very kind of intuitive. It minimizes the disagreement between the model output for the clean input and the noisy input, right? So because we want this, the intuition is that if the representation, which is the clean, free, noisy free samples, the representation of the noisy free samples and the representation of the noisy one, if these two representations are similar, their prediction should be similar, right? So we want to minimize the prediction distance. This is give us the extra performance gains. This is two heuristics we use. Overall, when we add all these things together, so we have, this is our overall framework, right? So we have the bottom module will generate the noisy samples, and then we pass it through a kind of a neural network with pairs, and it will select hard examples, and eventually it will be optimized. So in the experiment part, we apply these kind of techniques on 3 data set, which is this data set is a metaphor data set, the personifications, and the parallelisms. All these 3 data sets are about rhetorical figures. And in order to test the generalization of the proposed approach, we test on 2 OCR engines. Also, these 2 OCR engines, they have different error rate. So the first OCR has about 3% error rate, and our self-developed OCR, which has the 6% the error rate. And yeah, so here is the full result. I won't go through the details, but as you can see here, so first we compare with the kind of different way to generate the noisy samples, right? And also we try different way to learn from them. Yeah, so here this is the result. And also because we have 2 heuristics, so we conduct ablation study to show the effectiveness of these 2 heuristics. The first one shows the impact of the hard example mining heuristic, and the second part show the bottom part shows the improvement of the stability loss. And at the end, we also trying to see the generalization or the robustness of the proposed approach. We're trying to artificially increase the noisy level, and you can see here our performance, the model performance is pretty good at around now the 10% noises. When we keep increasing the noises, the performance drops quite a bit. Okay, so I just show you one practical problem we are trying to solve at all, but this is just one problem from the kind of the very huge pool of problems in real world educational scenarios. So here I will just show you another example. So so in this example, I will show you how to build a robust word recognition engines. So here I show you a paragraph here. So I can read the paragraph. So let's say, according to a research at the Cambridge universities, it doesn't matter in what order the letters in a word are. The only improvement thing is that the first and the last letter be at the right place. So as you can see, we as a human, we can understand this sentence. However, if we pay attention to the spelling of each of the word, we know they are spelled wrong, right? Only the first and the last letter are correct, and all the letter in the middle, they are kind of randomly shuffled. However, we can still read the sentence. So this kind of sentence is called the Cambridge sentence. If we throw those kind of Cambridge sentence into the Google translation system, it just breaks. The system just breaks. there's no way for this system to understand this kind of sentence, right? So this happens. This kind of things happen quite a lot in when students read their essays, right? So we cannot control, or we cannot make sure every student can spell every word correct. So in this way, so we are trying to develop the machine models, trying to capture those kind of special informations and trying to do the word recognition, which is kind of recognize and correct this kind of word, wrong, misspelled words. So if we pay attention to the problem itself, we can see here there are kind of two different kind of errors. Or this kind of error that comes from two things. The first is there's kind of dependence between each letter, right? So we can call it the word level, we can call it the character level dependence, right? Because the letters so every letter in a word, they have some dependence. The second kind of dependence is we call the word level dependence, because every word is in a sentence, and the word within a sentence should have some dependence. Yeah. So therefore, we developed models trying to capture these two different dependence. So here is our model. So within a word, within each word, we use a transformer to model the character level dependence. And within a sentence, for each word, we use the LSTM to model the word level dependence. So in such a way, we kind of build a framework we call the MULD, which is a framework for robust word recognition. So yeah, so for the details, you can please check our AAA paper, and I will move on. So this is the third part. In the third part, I will show you some very cool and robust educational multimodal machine learning application we built at Tao. So as we all know, due to the COVID-19, and right now we have offline classroom and we also have online classroom. There's no big difference. There's a lot of difference. There's a big difference between offline classroom and online classrooms, but the people are kind of accepting these two different modes of education, right? So the first application I will show you is about classroom activity detection. What it does is within a class, right? There are teachers, there are students. We are trying to identify for every frame of the classroom audio recordings, which part is spoken by the teachers, which part is spoken by the student. So this is a very important problem, and here I will show you a concrete example, right? So I took some pictures from our one-on-one classrooms, the offline classrooms at Tao, and we have some recording devices to record the entire classroom videos, and then we kind of extract the audio track, and then we pass it through the machine learning models, and we want to identify the spoken sentence, which part is spoken by teacher, which part is spoken by the student. So the first thing pop up in our mind is, okay, now we only have one teacher. We only have one teacher in this case. So we can ask the teacher to pre-record some voices from the teacher, and we can extract the voice biometrics from the pre-recorded spoken sentence from the teacher, right? Once we have the voice biometrics, we can do the matching. We use the learned voice biometrics to kind of match. Okay, so this frame is similar to the the voice biometrics. If similar, okay, it's spoken by teachers. The other one is spoken by the student. So this is kind of work actually. So and also we tried, right? So as you can see here, we have several vocal samples from teachers, and we also have the entire classroom recordings. So we first pass all this kind of the audio sample to the VAD models, which will cut this sample into some small pieces, and it will remove the silence part. Once we have this kind of small pieces of audio tracks, and we kind of learn trying to pass it through pre-trained the voice models, right? And now we get the initial vocal embeddings, and then we pass it through some sequential models trying to learn the sequential embeddings. And once we get all these embeddings, we do the matching part, which we can compute the cosine similarity and all the stuff. So this is actually it works. Once we have this done, we are kind of trying to think about can we make it better, right? So is there a way to make it better? So we are trying to think of another way to still doing the class activity detection task, but without the voice biometrics. We don't want the teacher to pre-record the vocal samples. So here, what we did is this, right? So we developed a kind of attention layer we call the multimodal attention layer. And it intuitively, what it does is, in our case, this is the recording from the offline one-on-one class. We know there is just one teacher and one student in the classroom. We know the content from their spoken sentence are kind of different because the teacher is teaching, the student is learning, right? The question, the things they said, the things they said are kind of totally different. So this is one thing, right? The other thing is because there are only two person here, one teacher, which is usually kind of much older compared to the students, and their vocal information is also different. So therefore, our multimodal attention layer, what it does is what it does is similar to the clustering stuff. It first uses the vocal information from the teacher and the vocal information from the student. And we use the kind of vocal information to do the clustering. Now we have kind of we have two clusters. We know one cluster contains all the spoken sentence from the teachers. The other set of stuff is the spoken sentence from the student. But we don't know which set is teacher, which set is student. And now we use the text information, right? Because the spoken sentence, the content that they spoke is kind of quite different. So we use text information to do the classifications and to say, oh, this set is teacher, this set is student, right? So this is kind of the idea of our multimodal attention layer. And this work is published at ICASP 2 years ago. If you want to see the details, please read our paper. The next application we built is called the teacher question detections. So for all the class at Tau, so we kind of require the teacher to always ask more questions in the class. As the previous research shows that the question kind of can inspire student thoughts, and it will encourage the in-depth classroom discussion. So we want teacher to ask questions, but there's no way to kind of guarantee the teacher really did that, right? So there are a lot of previous efforts trying to solve these problems. For example, people design some microphone for the teachers, or just put some device in the classroom, trying to record all the recordings. And also when the Kinect comes out, people are trying to put the Kinect in the offline classroom. People design some way how to, put multiple Kinect to kind of well capture everything happened in the classroom and so on. But all this stuff is they are handling some challenging problem in the offline classroom, but we cannot bring them to the online environment. So therefore, in our work, we designed an end-to-end question detection framework for the online learning scenarios. So here's the overall framework. So basically, what we did is, given the audio recording from the class, we first throw it to the VAD component, which will cut the entire voice into small segments, and the silence part are removed out. Once we have the small segment, for each segment we throw it to the ASR engine. We are trying to get the transcription, which is the language content. Then we use this language content to do the classification. It will decide, okay, so this sentence is a question, this sentence is not a question, and so on. Yeah. So this is the kind of the overall framework. So specifically in our case, in addition to decide which sentence is a question sentence or not, we also build a model trying to do the fine-grained classification on questions. After doing a lot of survey with our teaching professionals, we found there are kind of 4 types of questions that usually happen in the K-12 class. The first one we call the knowledge association questions. So basically, this kind of question is asking the answer for certain problem or certain knowledge. The second type of question is we call the open question, which is kind of like ask the student to how do you what's your thought, right? How do you solve this problem? The third type of question is the procedural questions. Because it's online class, usually sometimes the teacher asks them, can you hear me? Is your laptop correctly set? And all this stuff. This is called all the procedural questions. The last one is we call the management questions. It's a dialogue from teacher and student, and usually, people have some very short phrases. They are just used to manage the dialogue between teacher and student, such as the excuse me, something like that. So yeah, so once we have the transcription from the ASR engines, the transcription is thrown into the neural language understanding modules. So this is so we use the BERT as our backbone for the pre-trained models, and we fine-tune. We use our task-specific label to fine-tune BERT, and then we add a kind of a multi-class loss here to make the final prediction. The model will give us whether it's a question or not, and besides that, we will get which type of question it is. Okay, so next I will show you another application which is widely deployed at all, which is spoken language proficiency assessment. So what it does is we create a kind of a verbal fluency task. What that is, here we show you a math question, which is a very simple math question. For example, here the question is, if we want to cut a loaf of bread into 20 pieces, how many cuts do we need? Right? It's a very simple question. So in this kind of question, we don't really care about the answers. We care about how do you come up to these answers, right? What your thought. We want to see your thinking process. and we want the student to think a lot, which is you tell us how do you think. So the student parents, they just took a video of the entire process, the entire thinking process, and they will upload their video to our backend, and the teacher trying to kind of give them feedback. So here is a
我
example.
们来看这一题，这一题是切法式小面包，就是说，你看这个是切了10下，再加上原来没切的这一段加1，那就是11段。这一题是我一共有20段，请问我切了几下呢？是说我一共有20段。减去没切的这一小块，那就是减1，20减1等于19下，那就是我一共切了19下。
Yeah. So unfortunately, this is the real video is made in Chinese, but as you can see here, I hope you can feel what is the video looks like, right? So this kind of question is very helpful for the student, but it creates a lot of burden, the grading burden for the teacher, right? So you have to watch the entire videos and to give a feedback to student, give a score to these kind of videos. It takes a lot of time to watch this kind of video, right? So in this way, we kind of create AI-driven assessment tools kind of to create such videos, right? So our model works like this, right? So when the video passed in, we are trying to kind of assess this video and give the scores in these 6 dimensions. The first one is the verbal fluency, right? Whether the entire speech is fluent. And then is the topic relevance. Are you talking similar to my questions? The third is coherence. The fourth is the vocal emotions. Then the post interaction. Sometimes the question asks them to to show their full body, and we want to see their gestures. And the last one is the vocabulary diversity, whether your word is kind of diverse in your speech. Right. Yeah. So we build kind of we use all these state of the art deep learning techniques to kind of trying to do the grading for the 6 dimensions, and I also create some demo that people can try. If you have the WeChat, you can scan this code. If you don't have WeChat, you can visit our link, and they are there, and you can just try it. Okay. So next, so once we have the grading, once we have the scores for these 6 dimensions, we also want to give some textual feedback. We don't want to throw the 6 integers to the student to say, hey, this is your scores, right? We want to also give some feedback to the student. So the task is how can we generate this kind of sentence, how can we generate this kind of feedbacks? So what we did is here, right? So because we have text information, we have audio information, we have images here, because it's a video. So we kind of trying to fill these 3 types of informations. And what we did here is we have a gate called a modality gate. The modality gate will kind of control for each generated feedback, for each generated word in the feedback. So for each word, which part of the information is more important? It kind of control the information flow from these 3 different sources. Yeah, so this is kind of one of the key ideas in our models. And by utilizing these kind of things, we can generate feedback to our student, and we also run a lot of experiments showing that our generation model is much better compared to a lot of the deadlines, a lot of baselines. Also, we are trying to build kind of the dropout prediction modules for our online learners. So there are a lot of studies trying to study the dropout problem on the MOOC platform. So our case is quite different. So there are a lot of dropouts on MOOC, right? Because the video are pre-recorded, students have to sit here to see the pre-recorded videos. In our case, which is quite different, our case is live classes. We have the lab teachers, they are talking, they are teaching, and still there are some students trying choose to drop out, but the percentage is much more smaller compared to the MOOC stuff. So in that case, so we are trying to see if we in this kind of online environment, with the live teachers, can we identify the at-risk K-12 students? So details are shown in our EDM papers. Please see our papers. Okay, so in the first part, I will conclude and just talk about a little bit about the future outlook. So as we all know, right? So the development and the application of AI is bringing rapid change to almost every aspect of our life. But the education field changed almost have no change, right? To prepare, so and also we all know the AI is around us in the future, right? We have to make sure that our education and training is tuned to the new demands of the workplace and the society. So we have to use AI, we have to embrace AI, and also we have to use them, in our classroom, right? So yeah, so here I list a bunch of references I talk about in this paper in this talk. If you want to see more details, please check our papers. And in the past, we have created a data set called AI for Education, which is AI for ed.cc. It will show all the tutorials, all the international workshops we hold, and also it will collect a lot of AI events if you're curious about it. Okay, yeah, thank you very much. So this is my talk.
Great, awesome. Thank you everyone for joining us in this talk. I hope you've enjoyed it, and I hope you enjoy the rest of your day and other fabulous talks at our conference. Goodbye.